I chose the first twist of this series to be direct substitution because that is precisely the technique you should try first when evaluating a limit algebraically. Yeah, it doesn't always work, but when it does, it's remarkably convenient because you can calculate a limit very quickly. I have 4 limits here to demonstrate not only how to apply direct substitution, but also to show you how it can fail. Let's take a look at the first one. The number to the right of the arrow underneath the limit symbol is called the limiting value, and in this case, it's 1. Direct substitution is just a substitution. The procedure is to take this limiting value and plug it in for every x that you see on the inside of the limit. So let's go ahead and do that and see what happens. I get 2 times 1 to the third minus 1 plus 5. That reduces to 2 plus 4, which is 6. What you need to ask yourself after you've performed this direct substitution is, do I see a 0 in a denominator in my final expression? Now, my final expression in this particular example is just 6. There is no 0 in a denominator at the end here. And that indicates that direct substitution is working. In this case, we say that the limit is 6. Let's take a look at the second example. The limiting value this time is -2, which means I will try plugging in -2 for every t that I see on the inside of the limit. I get -2 over 2 plus -2, which reduces to -2 over 0. So again, I'm going to ask myself this question. Do I see a 0 in the denominator in my final expression? The answer is yes. There's my final expression, and I do see a 0 in the denominator. And that tells me direct substitution is not working. So in these first 2 examples, you can really see the difference between when direct substitution works and when it does not. If you see a 0 in a denominator at the end, then direct substitution is not going to work. If there is no 0 in a denominator at the end, then the direct substitution has worked and you've actually found the limit very quickly. Let's go ahead and take a look at the third example. My limiting value this time is 0, which means I'm going to take that 0 and plug it in for every y that I see on the inside of the limit. When I do that, it reduces to 0 over 1. Don't be fooled. 0 over 1 is just 0. It's okay to have a 0 in the numerator. It's only when there's a 0 in the denominator that there's a problem. So in this case, direct substitution is working just fine, and we say that the limit is 0. Let's take a look at the final example. The limiting value in this case is 3, so I'll try plugging in 3 for every x that I see on the inside of the limit. I get 3 squared minus 3 minus 6 all over 3 minus 3, and that reduces to 0 over 0. Remember, it's okay for there to be a 0 in the numerator. It's not okay for there to be a 0 in the denominator. So because I have this 0 in the denominator in this case, direct substitution is not working again. In the first and the third examples, we saw how awesome direct substitution can be. Because no 0 came up in the denominator, we were able to calculate those limits extremely fast, and it wasn't difficult at all. And this is exactly why you should always try direct substitution first. When it works, it really works. But as we saw in the second and the fourth examples, direct substitution doesn't always work. So what do you do when it fails? When that 0 in the denominator shows up? How do we proceed to calculating limits like in examples 2 and 4? For now, I'll just give you a hint. It's going to involve a little algebraic magic. When you're ready, join me in the next video twist to find out what I mean.